Right, so I'll crack straight on. So Paul's already covered a little bit of this, but I'm following the kind of standard AECOM presentation template. So a little bit about me. I've been in the industry for 11 years. I've worked in London since I graduated. Moved across from Belfast to London because that's just where I wanted to be and where I wanted to work. I've worked for AECOM for the last 5 years in their sports team, and I've managed to luckily work on quite a lot of pretty cool projects. The Curragh being sort of the most recent and certainly one of the ones I'm most proud of. But I've also worked on Al Janoub Stadium, which was called Al Wakra. It was the Zaha Hadid Stadium. If you Google it, you'll see it's quite recognisable. I'm currently working on a new third runway concourse for Hong Kong Airport, which is just absolutely massive and keeping us all up late at night at the minute. And then, as Paul mentioned, I've also managed to work away on the last 5 Serpentine pavilions, which is a small arts concept style pavilion that gets built year on year in the front lawn of the Serpentine Gallery in Kensington Gardens. And that's normally involving a new up-and-coming architect, and we kind of get a project from concept to completion in 6 months. So it's kind of a whole different ballgame compared to these sort of styles of project. So standard presentation, this is what you're going to hear about. See, the Curragh is quite a big project. I'm only going to touch on certain bits of it. If you've got more questions, please either, well, we can take questions throughout. Yeah, if you've got questions, just shout them out as we go. If not, have a chat with me afterwards and I'll try and fill you in. Some of my colleagues from the Dublin office have arrived, so I can point you in their direction for the ones I don't know the answers to. Okay, so for those of you who don't know where the Curragh Racecourse is, I've put a little point on the map. It's about, what, 50 miles west of here. And started off, so first recorded race was in 1727. The first Derby, which is the big race of the year, was in 1866, and then it became an official facility as sort of decreed by the government in 1868. So it's been the home of the spiritual home of Irish horse racing for the best part of the last 150 years. And the bottom picture on the right is the Queen Victoria Room and Grandstand from the 19th century, so you can kind of see where we've come from to where we're going. So the Curragh stands for the place of the running horse, and what you can see on the slide behind me is where everything was before the redevelopment happened. So you can see that we had a couple of old grandstands as well as parade ring, pre-parade ring, the turf club, Queen's Room, etc., etc. The development looks like this. So they basically wanted to flatten the existing grandstands, build a new iconic venue for the home of Irish racing, as well as reconfigure the parade ring and try and retain where they can. So what they I took that slide away. So there was a lot of work going on around the grandstand, which won't be covered as part of this presentation. But what we did do was we built a new museum and exhibition space with a new entrance area that then brings you out into a new parade room, going down to new pre-parade rings, stables, and a refurbished Queen's Room. I'm sure, again, if you've got more questions about that, Sarah and her team will happily answer questions for you. So the design team is a lot bigger than this. As I'm sure you can imagine, doing a project of this size and scale, there's more than just who's on the list behind me, but I've tried to kind of lay out the key players. So we have Grimshaw as the lead architect. They're based in London, which is conveniently close to where we were based in London as well. So they were in charge of all the early concept work. What they would do is they produce a whole load of packages, basically setting out the key concepts for all the different zones and areas of the building. And then you have NMA, who, well, may they rest in peace, who unfortunately went bankrupt September, who were the delivery architect and did a good job. So between Grimshaw and NMA, we worked between both. And then basically everything else was the AECOM machine landed. So structural engineer, MEP, QSing, project management, PDSP, health and safety. There's more, probably fire, facades, basically everything apart from landscape, which you can see is by Dermot Foley. Very loose project program, because I'm sure, as you can imagine, over a project of this scale, the program changed several times throughout. But we got involved in earnest in the summer of 2015 with the Stage 1 design. Working through 2015, 2016, And in early 2017 is when we got the tender packages produced. It went out to tender, started on site in August 2017, and then opened officially this year in May. So kind of moving on to the concept design, and this is kind of my favourite bit. So that's the Grimshaw concept. So what Grimshaw tried to do as architects is they tried to really use the landscape as part of their buildings. They don't want to kind of just throw something in that looks alien to the space. I don't know if any of you have been out to the Curragh. It's incredibly flat, incredibly windy. So to put something up there that didn't kind of tie into the landscape it just wouldn't fit with the area. So what they've got really is they've got three key planes. They've got the roof plane, they've got the landscaping plane, and in the middle they've got the terrace plane. And that's where everything kind of comes back to, and where was basically the starting point for all of the design. And then this is the a piece of art done as part of the initial studies whilst Grimshaw and NMA were still being appointed to the client. And you can sort of see how they were trying to blend it into the landscape, keeping the line of the roof plane similar to the surrounding trees, and how the landscape kind of bleeds in and belies the fact there's actually a 3-story building there. So materials, again, this is all coming from sort of Grimshaw's design intent. They had quite a really strong feeling as to what the materials were going to be. They wanted the roof to be doubly clad, top and bottom. They didn't want to see any of the structural engineering, unfortunately, in the roof. So it was clad top and bottom with a metal skin. They wanted to have a glass facade wrapping all the way around the corporate boxes at the top floor, so you could enjoy the views over the Curragh Plains unobstructed. As you kind of work your way down, they then wanted to start bleeding it more into the landscape, so they wanted the terrace and the mound to kind of just naturally bleed into the landscape around, whilst utilising sedum roofs and things where possible. And then finally, where we have concrete, they just wanted to express that honestly, so using concrete for what it's supposed to be used for, keeping it, doing it, detailing it nicely, detailing it simply, and exposing it. So still, whilst we were in our early stages of involvement, Grimshaw were working away, getting the extent of the roof optimised. And for a roof of this scale, it's obviously going to be the big ticket item. It's going to be where most of the cost is kept. So really, you want to make sure what you're planning and what you're detailing is correct. So what Grimshaw were doing is they were working away with MIT in the States, using parametric tools to help them optimize the shape of the roof against the 5 different parameters you can maybe just about see behind me. So it's kind of providing shelter from the sun, which I'm yet to see out at the Curragh, protection from the rain, and whilst also keeping shelter and shade to a maximum, but also making sure you've got clear sight lines and that you've got an efficient structure. So this is kind of what they ended up with. What we then did when we came onto the projects, we helped them develop the grid. So with a kind of sports structure like this, getting the grid right is important early doors, because generally where you're starting from is you're starting from the precast terrace, which tend to come in standard lengths. And that's driven, those standard lengths are generally driven by deflection, because you want to make sure that dynamically they're not too sensitive. So you start from there and you're kind of drilling back into, well, what's the space of the primary column grid going to be? How does that tie into the roof? And how does that, say, tie into the other bits and pieces of the architectural detailing? So you can see here we've got lots of different 6-metre grid options. We were asked to look at a 7.5-metre grid. Then the architects decided that they wanted the corporate boxes on the top floor to be set on a 6-metre grid, which is obviously incompatible with a 7.5-metre grid, because you then have a column in the middle of the facade in your corporate space, which is clearly not what you're aiming for. So we realised, right, well, let's keep the columns on a 6-metre grid so we can keep the structure down. And really it was a case of what worked for the project in terms of the column spacing at the lower level. So we looked at options where we introduced tree columns to keep the span of the structure at the first floor reduced. We looked at having columns on a 12-metre grid, effectively providing the same sort of support points to keep the structural grid down again, and then columns at 6-metre centres. All the while it's kind of going through iterative loops to see what the effect is, and what we came to the conclusion with input from Grimshaw was that keeping everything on a 6 metre grade, minimise the number of transfers, both at roof level and down in the main precast concrete frame. I'll touch a little bit later on as to why we use precast, but when the decision was made to go precast, those of you in the room who are used to dealt with precast before know that trying to detail it like steelwork, we've got secondary beams coming onto primary beams, really isn't a good idea. Everywhere you've got a join, you need a column. So in order to really simplify the detailing, keep the cost manageable, it was like, right, let's go for a 6 metre grid. That then went up to the roof, which meant that every cantilever truss was supported on a 6 metre grid with a firm support. You're not looking at, say, having a cantilever truss spanning on to primary structure between columns, which would have made keeping the deflection limits difficult to keep together, because again, I'll touch on it later, but one of the key drivers from Grimshaw was they wanted this flat edge all the way along the edge of the roof. That was their key clear driver of this razor sharp edge. If you've got everything that's spanning, has a multiple load path back to the rigid supports, it's going to be much harder to stop everything from visually sagging. So you can see how it all works together in this image from, I think, our stage 1 report, where we've got the roof structure coming down onto the columns, which then comes down, which then helps drive the set out of the terrace. So coupled with that was our very initial constructability assessment. And again, this is something on sports projects that really gets brought in to into play much earlier than you would maybe do on a sort of standard job. Whilst we had a big site, the Curragh wanted the racetrack to remain operational because it's not just a racing venue, they gallop horses there during the week, so they wanted to make sure that the construction work wasn't going to impact on that. So it was a big site, we had limited space for cranes. We needed to make sure that what we were specifying in terms of weight could be lifted by the cranes, manoeuvred and dropped into place. So this is what we started to work on in parallel with the grid option studies, making sure that when we were lifting up sections of the roof that the weight of that would be okay for a crane to actually get up and lift into place. So moving on a little bit into design, I'm probably rattling through this. So the grandstand is split into 2 main sections. We've got the main grandstand, which is in yellow, and behind is sort of entrance, access, atrium space in green, and then the roof outline dotted in blue above, so you can see kind of the extent of the roof compared to the grandstand. And this is just the grandstand in an isometric view. The grandstand itself, again, it's precast concrete. For part of precast concrete, you want to make sure you've got a lot of repeatability in there because that's where you get your savings from modularization. We have that in the main grandstand space. The atrium, unfortunately, we did not, but we tried our best to modularize it as much as we possibly could. The grandstand itself is 140 odd meters long, so it had to be split with the movement joints. So you can see we split it into 2 sections, one that's 50 meters long, another one that's 90 meters long, and each was stabilized by 2 opposing cores. The opposing cores helped for keeping our torsional deflections down, but proved quite tricky when it came to sequencing and thermal lock-in when we were considering the fact that you've got a roof on top of this that wants to expand and contract at the same time. So why precast concrete? We asked this question a lot during design, and especially as we got into the detailing, and especially once we got onto site, as the contractor over and over again was asking us why have you done this in precast? We could have done this in situ and it would have been great. The simple answer is that during our feasibility studies in 2015, concrete, and especially precast concrete, was proving more economically viable than steel, according to market conditions, which I've been reliably informed that there was a formwork shortage in Ireland in 2015, which meant that everybody was moving away from in situ and into precast. That's been refuted from various different people I've spoken to, but that's the advice we had at the time. But we were able to benefit from the other things that precast concrete can bring to the table, so we're able to really use the fact you can get an exposed high quality finish made in a factory. You can benefit from the modularity. We do have a spacious site. Whilst the access at the front was restricted for crane deliveries, we did have space at the back, so you could be bringing truckloads of concrete from the precast factory, stacking it up and building it as we needed. There was no formwork required. Detailing meant that it would simplify the follow-on work, so you're not having to strike any formwork, and then once the precast was up, you could get in there and you start getting your walls built, get your services up, and just meant that everything could kind of happen in a more overlap sequence than perhaps would have been with in situ. Concrete's obviously very durable. You don't need me to tell you that, as well as its thermal mass benefit. What was interesting about the project is, certainly in our experience, if you're going to go down a precast frame route, you'll get your specialist subcontractor on early doors, certainly before the contract goes to tender. That wasn't the case with the Curragh. It was let under a standard Irish government form of contract, which meant we got it right up to the end of stage 3 and 4, and then the precast subcontractor was appointed to the main contractor, so we weren't able to mine any of their experience knowledge until we'd already gone to tender. So I just thought it was quite interesting to show you what we had proposed in terms of the main beam to column support details versus what the contractor ended up building, and I'll explain these in a little minute. So with precast concrete, you're obviously having to build everything onto corbels, either exposed corbels down below the down below the beam where we had space with the ceilings and it wasn't exposed. Where we had exposed concrete, we're looking at using half lap joints, and occasionally we were specifying Pico specialist proprietary connections. The contractor wasn't keen on Pico connections because there would have been hundreds of them, and they weren't keen to pay for that. So what they ended up proposing in the end, and I don't know how clear this is a plan view from the top. What they actually did is they broke the columns at each floor and landed 2 of the beams right on top of the column, and then brought the other 2 in on just steel dowels that were hanging out of the 2 precast beams, and then threading the columns through together was a whole load of big reinforcing bars. So section 1 in the middle here, these are the 2 beams in red that land on the columns. So the columns were 500 diameter circular columns. They're bearing about 200 mil either side, with a grout tube and a void left for the bars to come on through. The column above was then whizzed on with standard Pico column shoes. And then the detail for the incoming beams, you can see just a cast lump of steel effectively to act as a pure shear dowel to pick up the columns. So that was an interesting process to go through as a designer rather than as a contractor, to really see how in the world of precast, Banagher, who were the precast subcontractor, did their detailing, and certainly be lessons learned kind of going forward. One of the more difficult things to resolve in the precast frame was the first floor atrium level. So despite it all being precast, which sets itself up very well for being stacked on top of each other with big downstands, the architect wanted to have a flush finish between the beams and the slabs, so there was going to be a bit of a payoff between economies of scale. What we ended up doing was specifying really wide and really shallow beams that were only 350 deep in the end, and specifying a sort of form of an omnia slab where the contractor was casting their own 200 thick precast biscuits with casting angles in the end that could hook over the corbels hanging out from the beam. Then they'd pour structural topping on top that kind of brought it all together. And the image on the right is what we ended up with, and I think I'm quite pleased with how that ended up in reality, because it was one of those difficult things. As it got, if you realise the beam wasn't working and we needed to make it deeper, the load on it got more because the slab coming in was getting thicker as well, and there was never we couldn't figure out a way of getting, say, almost like a suspended ceiling to work within a void form or something weightless and then a slab on top. It was just a very tricky thing to try and sequence, because with this was kind of quite bespoke precast as opposed to just picking up your catalogues and just picking what you want from there. So that was probably the second most difficult thing. The most challenging thing was the interface with the roof. So the way we designed the precast frame and the roof was we had separate analysis models, because you couldn't design everything together, you couldn't run everything together. But we had to bring them together at some point, and steel with concrete detailing is obviously quite tricky. because we had the steel roof that was acting as a massive flappy sail in the wind, transferring a lot of very strange forces into the reinforced concrete frame. And bearing in mind, if I scooch back to this image, we've got our stability elements all at the back of the grandstand, and the roof kind of sticks out from the front. So there's a lot of torsional twist things starting to come into play whenever the roof was brought into it. So with lots of different details kind of worked out as to how we're going to basically anchor the roof down in places, because it's a cantilever, it's acting as a push-pull, so generally under its own dead load, all the columns on the front are taking a massive amount of force down, the columns at the back are going into uplift, so it was really a case of keeping the roof down, pinned down, rather than being worried about its compression. So this is the detail on. This detail here is for the column on gridline C4, which became quite notorious for all of us, because it's the column that supports the edge of the 40-metre span cantilever and ended up supporting about 30% of the roof in total. So that's both down and up. So this is a column that could actually go into uplift. So we had to design a massive cast-in assembly that would drop down into the top of the column, that the base plate could then be bolted to, and in the case of a massive uplift, it could keep it there. So that was designed as a zero movement joint, and then as we go across, we have different concrete slab to precast roof details, with different precast details to steel roof connection details going on across the building. And depending on we did a lot of sensitivity studies, and depending on what basically we get away with releasing laterally, we did. So we wanted to make sure that the roof wasn't fixed laterally everywhere, else we'd be getting a lot of sort of minor twisting effects because of the moments not shedding properly. So that there was a lot of kind of backwards and forwards, toing and froing, and then seeing what we were left with and how we could actually physically make the detail. So a lot of the time we were supporting the back span of the roof trusses on top of 300 wide core walls, or where we couldn't get that to work, we were putting downstand beams in. All of this was being done in precast concrete, so we needed to make sure that the coordination and the thought and the detail was there, because it had to work. There wasn't the case of it's all going to be done on site in situ, so we can kind of work it out once we get there. It has to be figured out before the precast is made, never mind before the steelwork is made. So what we did, we had the models separately, and then when we needed to, we brought them together and did our various sensitivity studies, and it's still standing there, so we hopefully got it right. I'm rattling through this. So the roof design is where I'll try and focus more of the fun, or more of the detail on, because that's, to be honest, where what everyone sees, rather than the nice grandstand. So this is just a view from our Revit model, which I think is quite nice. This is a plan of the roof, so it kind of shows you how the trusses were laid out. So typically we have trusses that span 26 metres, split between supports at a 10-metre span, so 36-metre trusses with a 26-metre span, and they repeated along the majority of the roof. So we got our benefits of modular construction there, because Kiernan Structural Steel, who did the steel fabrication, could just build that one truss, I think maybe 8 or 9 times, so they got pretty good at that one. Out to the west is where we had our big cantilever, and it spans 40 metres from the first column support. So that's what drove the depth of all of the trusses, and I'll show you on the next slide what we got away with. And then over on the east side, we didn't have as big a cantilever there, simply because that's not what the architects wanted. So this is sort of a quick comparison to scale of how far the trusses all spanned. So we've got the truss, the west spine truss spans 41.5 metres, and then going down to the standard truss, which spans 26. So you look at the 26-metre span truss and think, well, actually, we're not asking it to work that hard. In reality, it's 3.5 metres deep, so its span to depth is about 7, which is about right. But as we're getting out to the spine trusses, we're kind of pushing it more to 8.5 and to 12, which took a lot of it took a lot of working out because there's a lot of things to balance with that. Because not only have we got to get it right for our ultimate state design, our strength design, we have to get it right for deflection. So ultimately, the trusses, the simple spanning trusses, are going to be deflecting a lot less than the truss on the outside. I was doing the numbers on the way over. We got the steelwork in the roof worked out about 130 kilos a square metre. For those of you who like your facts and figures. So I kind of touched on it about the cantilever leading edge. So this is the sort of deflections that we were getting at one stage, I think. This is an old version of the model where the deflections are 214. I think by the time we got to final detail design, that was more like 400. And what the architects wanted is they wanted this leading edge to read exactly flat. They didn't want to see it drooping in the corners. So we had to work quite hard on that to figure out how we were going to achieve this and how we were going to achieve this detailing, which is making sure that this point at the end remained flat whilst hiding a gutter that needed to be able to drain to its down points, as well as making sure that all the cladding and everything else would interface in with it. So how we did that was we did a lot of work on construction sequencing. So not only kind of working out the weights of modules being lifted into place, we were figuring out the order in which they were going to be brought in, because we were trying to design this as unpropped. So you can imagine if you've got a 40 metre spanning cantilever, if you're going to build a temporary tower up kind of 20-30 metres, that's quite a constraint to put on the contractor. So we're trying to find ways of making sure this was possible. So what we did during the design stage was we proposed a construction sequence which basically started at the east end and started at the east end, went east and then went back west. We obviously couldn't start in the very corner here because you've got no backspan on the trusses and you just have something flapping around. So we had to be able to basically build the anchor point for the cantilever trusses going east, which you can see here. So you've got the green is the initial first phase, then phase 2, phase 3, phase 4, phase 5, phase 6 as everything gets built in. That can then start to be clad as the steelwork progresses west. And in a similar way, we got to the west end construction sequencing and did the same thing. So what we were able to do then was to see what the impact of the build sequence was and how things were deflecting and how things were moving, and critically, if we were developing any locked-in stresses anywhere. With a cantilever roof like this, the build sequence isn't really changing the load path, but on other projects, if you're, say, lifting a big arch into place, you might find that it's you're expecting it in the final case to behave one way, but during the construction it's going to behave a different way, and in reality you might find that it's not going to ever get to the point you assumed as part of your linear analysis model. So what we were trying to make sure is that we had our sort of linear analysis model where we'd turn gravity on in one go and everything would just deflect, and we'd have our construction sequencing model where everything was built up incrementally, and we could compare the deflections, we could compare the forces and see, okay, good, the final load path is similar to what the construction stage load path is, so we know that our construction sequence isn't having a negative impact on the design. So how we communicated all of that to the contractor was through drawings like this behind me on screen. I know you can't see the detail of it, but what that is a whole load of presets. So going back to the constructability assessment, where we're looking at what was the maximum size of elements we could bring into place. We're then looking at where the splices are going to be and telling the contractor what presets they need to allow to basically build the roof, build the next bit up at an angle so that when it deflects onto itself weight, it deflects back down into its final position. And what we were trying to do was make sure that we'd taken account of all the deflection or all the weight that's going to be there in the permanent case, so mainly self-weight and the weight of the cladding. We did this ourselves as part of the tender process to let the contractors know this is a complex roof, you're going to have to do your own work on it, and then we worked with Kiernan's to help them develop their own construction sequence, because what they actually did in the end was they did prop this corner of the roof. They did end up propping this corner of the roof, so they did slightly change the load path. And instead of presetting everything like like we like to think everyone can do in a design office. They just whacked a whole load of shims and washer plates in to actually just kink everything up on site. But it's good to know how things are done in practice so that you can at least be aware of it, and if it is that important, you can be making sure and stopping work if needs be. So as I was chatting before this started, so when we were doing this back in 2015, 2016, it was kind of semi-leading edge. It's kind of a lot more commonplace now, but what we were doing is we were developing the geometry for the roof as a parametric model, using Grasshopper to control it. So we were working together with the architects who were generating their surface using the same parametric tools, going back to the 5 key constraints that they had. So they would deliver to us a surface, and then we'd run our script on it that would generate our roof structure for us once we had set out the initial parameters. So what that allowed us to do is we were able to go through a lot of rapid prototyping, where the architects could send us a new roof surface. We could generate a new structural analysis model, spit it out into our software package, which for this one was the engineer, and start to run some size and testing on it. So instead of having to kind of look at something, maybe scheme up one truss and start to apply some engineering judgment to it, we could actually take the whole roof and with a couple of clicks of a button actually have it designed to a certain level to give kind of guidance as to what's the better option to take forward. And this is something that we do just on our projects now. So the likes of the Hong Kong airport, Serpentine Pavilion, we try and script as much of it as possible, because it just means you're losing less time in modelling. So what tools like this can do is you can have the model generated in one place, and then you can just have various outputs. So you can spit it out to your analysis package, you can spit it out to Revit, you can spit it out to Tekla, you can spit it out to wherever you need, so you're not having to ask 3 different people to model the same thing off 2D drawings. You can just be creating it once and away you go. I mentioned about roof steel design optimisation, and given this is a room full of people who are affiliated with the IStructE, you'll be obviously very aware of this paper that was in, I think, October's issue? No? All right. So the Universities of Sheffield, Bath and Edinburgh have been working away with funding provided by the EPSRC to develop a design optimisation tool, which they have just released, and it's called Paragreen. Anyone who's familiar with grasshopper and rhino will realise that everything's named after an animal of some description, so they've decided to choose, I think it's a penguin. And it's pretty cool. I would honestly recommend go and have a read of the paper. It's in the top right. I can email it to you if you like. It basically just does it's that kind of one-click button that everyone's been kind of aiming towards, where you throw in what your constraints are, so what your support conditions are, what your depths are, what your loads are, and it will work away at what is the most computationally perfect solution, and then it'll work back from there to give you something that's actually buildable. So we help with the development of this, because we've got links with Sheffield and Bath. So they were looking for an exemplar project to run this on, and we're like, hey, we've got some long span trusses we could do with some help with, so we give them the Curragh to run with. Obviously this was back in 2015, 2016, they've only just released the tool now, so the information they gave us back we couldn't really use, because it couldn't pull in all the other constraints that we have, such as that the roof is quite heavily serviced and has effectively it requires access through, so we couldn't be throwing diagonal bracing in everywhere to bring the different load paths through. But if we were to do the project again now, we'd be using tools like these to help us with our optimization process and bringing it back into the parametric design workflow we have. We don't have to do this just for kind of complex long span roofs. If you've got any kind of structural grillage, you can have a bit of a play with it, and it just might throw you up an option that you haven't thought of before. And it might be utter garbage, or it might be the one you end up going with. So going back onto how the roof's stabilised, it's effectively a Veerendale truss on plan. Each of those red boxes are a series of brace bays. But again, fairly simple, all tying back to the 2 cores, but you can see where the cores are dotted in, against where the bracing goes, or where the bracing lines are. It moves a lot in the wind and under thermal loads. So the moving joint position was quite critical. Ideally, we would have wanted more, but we didn't have enough stability elements to get away with it. So we just had to detail around it. Detailing. So I showed you how the precast guys did their detailing. This was quite an eye-opening process as to kind of, again, office-based steelwork detailing versus fabricator-based detailing. So where we're coming at is that, you know, we're used to working on sports projects where we have a lot of exposed steelwork. So we will generally try and detail an architectural connection. When the contractor gets it and realizes that, oh well, this is all going to be hidden away, we can detail it differently. No one way is wrong or right. It's ultimately the contractor that's got to build this thing, so you have to rely on their expertise and their knowledge to say, you know what, detailing it the way they have is easier for them to do with the machinery they have available to them. To give them their credit, this is an incredibly complex detail. So this is actually the East End. The East End smaller cantilever. The reason why I've picked it is because I've got a photo of it. You can see me there for scale. So I'm 6 foot. So you can see the size of the assemblies that we're talking about. I think these ended up being something like 10 to 15 tons all by themselves. So there was a lot of kind of backwards and forwards over this. But again, I was giving the contractors their dues. They've got a single support point for 3 lines of primary structure, all coming through together. So they worked out a detail that worked for them and their processes, and it works. For those of you who are interested, they use IStructE for their steelwork connection detailing, which is the first time we've come across it, and certainly it's something we're looking at implementing if you're into your steelwork connection detailing. So on to the final bit. I think I'm getting through this quick. Okay, no, we're all right. So construction I've mainly got lots of pictures to show you. So I figure by now everyone wants to see pictures. So again, the construction team I have summarised. There's obviously more people than this, but these are the key players as far as I'm concerned as a structural engineer. So with John Sisk and Sons, we're the main contractor. They were one of, I think, 5 or 6 tenderers, and it just worked well. And Sisk's, I'd happily work with them again. They were able to pick up their team from Parkway Queeve in Cork and transplant them to the Curragh, which worked out well for everybody because they just designed and delivered a stadium and picked up all their lessons learned and went from there. And then Precast, it was Banagher Precast, who are out in the west, near the west coast. They were brilliant. It was really good working with them. And then with Kiernan Structural Steel, we developed a good understanding, a good working relationship with them in the end. But it took a little bit more because the precast was very, in terms of what Banagher were used to, it was very standard, very much what they were used to. Kiernan I don't think there's many steel contractors in Ireland who have designed a 40-metre cantilever roof. So again, to give them their credit, they worked it out and we got there together. So on to construction, and then so part of the fun with developing everything off-site was when we got to go and see some factories and actually go and see how these things are made. So we had 2 trips out to Banagher and we had 2 trips out to Kiernan. That shows my naivety. I was on the way to Banagher Precast. I just got to Dublin Airport, hired a car, and just put Banagher Precast in, just let Google take me there. And I was getting really concerned as the signs were just pointing towards a town called Banagher. I was like, this doesn't seem right, because normally, you know, all building companies are named after a person, right, rather than the town in which they're from. So I had a bit of a panic, but eventually realised that, yeah, it's just named after I don't know what came first, whether the town came first or the precast factory came first, but they've got the same name in case you're ever wondering. But it was really interesting to get out there and see their processes, because we would have loved to have engaged with the precast. As soon as we knew this was going precast, we'd have loved to engage with somebody, but because of the form of contract, we couldn't bring anyone onto the design team. We just had to kind of work it out the best way we could. So once we were able to start talking with Banagher, it was really productive just to see how they do things. So what you've got in the background is all of their column molds. for all of the precast columns. I think they were quite excited because they got to buy some new moulds. And so this is where they basically formed every single column for the whole job, and by bringing their expertise in detailing into play and splitting it at every level, it meant they could actually cast everything inside rather than, say, casting a whole 15 metres worth of column outside, which they could have done and brought it to site and then had everything fixed into the side. Like, well, no, we'll break it down into 4 or 5 metre lengths, then we can do it inside, splice everything together and take it away from there. And then just, we're there to basically check the processes, see lots of concrete cubes, see lots of heavy steelwork reinforcement detailing. It's always fascinating to go and see your RC details actually being built, and you fully appreciate what an M25 bar looks, or a B25 bar looks like compared to a B12, and you can see why people get a little bit upset at you. Similarly, going to Kiernan was eye-opening, because they've got a big facility, but the size of the Curragh trusses were just something else. So you see the truss here set up right at 3.5 metres deep, and then just all the details that go with it. So you can start to see some of the node connections at the corner columns, as well as some of the base plate details with the shear keys. And then onto site. So because we were based in London, we couldn't get across the site as much as we could, so we worked closely with our Dublin team, who helped us out a lot with going to site and reporting back. I think they did their best to put the fear of God into CISC whenever the London team were coming. They were always terrified when we arrived, and we were just pleased to see progress. But it was amazing kind of seeing the site come to life, because obviously most projects spend forever in the ground getting the substructure done, getting all the groundworks, getting the earth shifter around, getting all the first services in. But it was amazing kind of seeing the stuff go up. Like, we'd be on site and they'd have a whole level of cores done in a day, and that was the beauty of precast. We were all just kind of waiting for the precast to come, and then once it came, it was great. It was an issue for us at the start of the job, because normally with a concrete job, if it goes to tender and then construction, you've got a long lead in, because all the contractor's really worried about is getting their RC detailing done, and then the concrete happens on site. Whereas Banagher needed all their stuff on day one, because they need to get this into the factory so that it would be coming to site when it was needed. But I think we reaped the benefits of it as it came up, and again, just seeing all the pockets and things they had to leave out to get all the beams into place, and how all that worked was just fascinating. They did all of their detailing in Tekla, strangely enough, even though it's a Steelwork design package. So they had all of their bars, all of their casting assemblies, all their different bits and pieces, which you could all review as part of their factory assembly, which was again a really clever use of 3D BIM. Going up the construction, we got the precast frame. So by this point, it was starting to rocket up, because it was stick built, and you can see the starts of the what would be the Great Hall, where we had all the exposed concrete as a double height space, where they put all the tope bedding stalls and the escalators up to the upper floors. Kiernan were champing at the bit to start getting the steelwork up, so you can see the steelwork was starting to go up in parallel with the concrete. So there was a bit of a race on to keep the concrete far enough ahead of the steel, so that they wouldn't start to come across temporary stability problems. So yeah, you can see the steelwork balconies going up, as well as the steel roof. Other bits and pieces that I've not really touched on as part of this presentation, but there was a lot of fun brickwork details that the architects wanted to bring in. And again, I don't know how many of you have attempted to design perforated cladding, but there's not a Eurocode or a British standard that can help you out with that. So there's a lot of backwards and forwards, a lot of testing, a lot of justification for this, which our Dublin team thankfully stepped in to help with. And then a lot of the facade cladding stuff also was going up in parallel, and again it was all the finishing touches that really give this its finesse, because if you go out there now, you'll not be able to see any of the steelwork detailing, which is fine in my book, but because the cladding is done to such a nice detail and such a nice finish, that's where all the focus was put. It's like, well, how can we make sure that we're going to give the the detailing the attention it deserves. And here's the steelwork detailing going up. Again, you can just see the sheer scale of everything. For context, that column's a metre wide. That concrete column, that's about 4 metres. Everything's big. Again, you're looking at things in a 3D model, you're looking at things in a piece of analysis software, you don't really understand the scale of it, appreciate the scale of it, and then you start to see things go up, you're like, wow, yeah, that's big. The atrium at the back I've not really touched on. I apologise for that, but I think that the more fun is in the grandstand. But the atrium is where we had a lot of the really nice detailing with the concrete. You can see where we have like the joint lines all lining up and coming through, and that was something that Grimshaw were really keen on. If you're gonna expose your concrete, you need to be all over the detailing and the joints and how it's all going to match up, because if it's done badly, it's just going to ruin the thing, or worse yet, you've got to go back in and cover it all in ceilings and cladding, which just ruins everything. We had over the atrium, I'll touch on it very briefly, a big light well, and we came across some construction issues with that, where the beams themselves are quite slender, and were always designed that they wouldn't be ever exposed to thermal radiation because the glass would take care of that. But what we found during construction was that the sun was rising, warping everything, and then nothing would fit. So they had to put these, they ended up having to put what was temporary restraints in, became permanent restraints, just to keep everything aligned, because obviously the glass is all quite sensitive and needs everything to be just so. And you can see in the background sort of the escalator and the stairs, and again, that's all just, it was interesting trying to detail all that with precast, because you just need information at different times. Because normally with in situ, you can be working that stuff out on site when maybe say the escalator guys have already been appointed, but when they haven't been, you're kind of just relying on standard details and allowing enough tolerance so that really it can fit anything that they're going to propose. So that is basically everything I've got to say. This last completion slide, on the top are the images, renders, and on the bottom is the final construction, or the final on-site photos. I think I always like getting a project to this stage where you can kind of hold up the planning render and go, wow, it just looks just like that. And we're really pleased that we've been able to get the level of detail and the finish that Grimshaw wanted, and we all became quite protective over, especially the razor sharp edge on the roof. It really adds the drama and the effect that the architects were looking for. That's it. So, does anybody have any questions?
In the wind modelling, did you have to do it on cantilevers, or?
We took a code-based approach. So what we initially, cantilever roofs are actually quite well covered for in Eurocode. So what we did was we took a stab at the philosophy, and then we sent it to RWDI, who did their own desk-based study on it and basically verified what we'd come up with. So basically just looking at it as a block cantilever, as an open-ended cantilever, and the code-based approach was all we needed in the end. I think had there been generally a code-based approach will be conservative, and I don't think the feeling was there wouldn't be enough savings to justify doing a wind tunnel. So that's, yeah, it was just a code-based approach.
Was there any concern with the dynamic effects of
we considered that, and we tried to keep the natural frequency to about 1 to make sure that it wasn't too dynamically sensitive. And had again, we pushed it out to different people to get their opinions on, and we had quite a long debate with a professor from the University of Cambridge who wanted us to design it as a bridge. But you kind of have different people look at it differently. But typically for a long span cantilever roof, we know for about the 1 Hertz mark, we're generally okay.
Anyone else?
You mentioned the thermal lockout between the roof and cores.
Mm-hmm.
How can you elaborate on that? How you dealt with that at the moment?
Well, the movement itself was dealt with at the primary movement was dealt with at the movement joint, but in terms of where we released, yeah. So let me see if I can. I've not got an image that will help me. But typically, what we did was that. So you can see the cores in red behind me, and you can see the primary grid lines. So everywhere you've got a primary grid line, you've got a truss coming in, and then you've got the corner, the big truss on the corner was coming out from this point out to here. So you had a sort of interface point back here. What we tried to do was we tried to make sure that we used the cores as a couple. So we're generally locking one truss in on each, so we weren't having kind of a miniature push-pull on each. So say we would have had this truss locked in and this one released, and this truss locked in, and the spine truss locked in, and this one released, and we would have had them released in certain different directions as well, depending on where the stiffness of the wall was. Because we had, say, we were missing capping slabs in places, so we didn't really want to be putting too much minor axis bending into the core walls. So if that was the case, we released it. And it was a case of kind of establishing an overall principle and then trialing things. So what we were finding was if we released a support, it was actually moving 2 or 3 mil. So there was no need to actually detail that as a movement joint at all, because the size of bolts and castings we were using was a 3 mil oversize anyway. So we would have got the movement out that way. So we're just trying to cut down on the complex detailing, because every single one was different. It was either coming down on a core wall, column, a transfer beam. So it all required a different approach, which when you're trying to do design, you want to try to be standardizing as much as possible. So that's what we tried to do. I've got some drawings on my computer. I can put them up later if you want to have a look in more detail.
Yeah, Paul.
Michael, fantastic presentation and congratulations. And probably for us here in Ireland, it's one of these structures that it's kind of once in a lifetime opportunity, but for yourselves in the UK, probably working internationally, you get many opportunities like this. Was it considered or designated a consequence class 3 structure?
For robustness?
Yeah.
Yes.
And did you have fun? Any fun with that, or would you like to?
It's a very good question. I should have put something in the presentation about that. Because so from the precast side, that was a big learning curve, because obviously precast, you don't have the same inherent robustness that you would have from a concrete frame. So there was a lot of reading into what typical robustness detailing is, and unfortunately it was all quite contradictory. So we just had to come up with a strategy and go for it, which is basically just making sure that the slabs and the beams were all tied together at the end of the day. For the roof, we designed certain bits as key elements, but what we try to do on projects like this is make sure we start to look at where elements are highly stressed, and where they're highly stressed, we'll remove them and start to investigate alternative load paths under a collapse event. It's not strictly in the code, but it's what we like to do just as good practice, because you don't want to, say, lose a diagonal somewhere and the whole thing just to crumple down.
And is your approach generally more so the notional removal, is that your first approach, or do you look to key element design before you go to notional removal?
It really depends, because I mean the key element, it depends on the scale of the project, because you've got your key element. If you're going to lose more than 70 square meters, then it's a problem. But if you're knocking out, it really depends. But the notional removal is something we always try to do, regardless of whether things are key elements or not. Say for instance, like the big column on C4, you can't design that for everything. So we're looking at ways of introducing kind of traffic calming, because what I've not touched on as part of this is the at level 0. That's right next to a loading bay, and so there's potentially a runaway lorry could come into it. But I would say if that actually happened, the lorry would be in worse state than the column would be, simply because of the size of it and the load coming down it. But yeah, typically we'd look at load element removal rather than anything else. But I mean, typically all the connections would have had your standard 7,500 kilonewton axial force, but given it's a trussed roof, everything's under axial load anyway, rather than typically bending and shear.
Yeah, Victoria. Sorry, not completed. Victoria, yeah.
The connections are pretty impressive. They're obviously really substantial. It probably wasn't something that governed given that it's a cantilever roof. But I wonder if you had a feel for what the self-weight of the connections was as a percentage of the overall weight of the steel elements.
Sarah's laughing away. This rumbled on for quite some time, would you believe? Because there were, what's the political way to say it? It wasn't properly accounted for during the costings.
That's why I'm asked that question, because I don't call out my performers.
Yeah, and again, it's something that we internally as AECOM will learn from, because in this case, sort of applying, we informed it one way, and it was interpreted a different way. So, like for the cantilevers, we were saying allowing a 20% steelwork allowance for the standard 10. That got rationalised to a nice even like 12.5 or something, and didn't end up being quite what we wanted. But we kind of there were a few discussions held about sort of the change in the detail, especially on the corners where the amount of, say, fabrication was reduced to simplify the detailing, but it meant that weight was added. So there's that kind of give and take. But yeah, you can never get connection detailing right. The only way to get it right is on a remeasurable contract. But I think since we've done this, there are kind of connection packages that are becoming more commercially available, and the likes of Statica is something that works well with all of our analysis packages that can allow you to do a scheme design on connections at an earlier stage, so you can be at forming the QS a more accurate number. But yeah, the connections tonnage rumbled on and on and on. So obviously we needed to make sure that we had the right allowance in our model for weight on top of everything else, given we were so precious about making sure it was deflecting just so at the end.
Thanks. This gentleman here.
Yeah, you showed your precast column connection earlier, where you stopped at each floor and started again. How did that work when your columns were potentially in tension? Where we got here, so we had these great big socketed dials there was basically a big reinforcement bar coming out from the column underneath that slotted through a hole in the beam, and then tied on with basically a bolted connection at the base. So it was all the tension was just going straight through the rebar. Just through the steel.
Yeah.
Yeah.
You write that you have a beautiful roof, like a big cantilever, which is coming down, and then underneath you have a big glass, the same. Also, how did you make sure that the connection of the glass was perfect?
Yeah, that's another good question. I should be noting all these down so I can update the presentation. So this shows it quite well. So we had what I didn't really touch on were the balconies at the third floor, where we've got quite a big cantilever coming out. So this is an old sketch, but the concrete stopped here, and then we had a steel cantilever bolt on after this. What we made sure was that these hangers were always in tension. So when we brought the steel and the precast model together, we were always making sure that there wasn't a case where the roof was deflecting down by more than this cantilever was, to make sure that it was always going to be in tension. That did change whenever Banagher came on board, because what we had initially proposed was that this precast beam would just be simply supported between the two columns, and then there'd be a separate precast beam that we simply supported between the column and the hanger, and then the steel balcony cantilever off that. Banagher wanted to cast this in one 14-metre long section, simply because it's easier for them to erect and would be require less temporary propping. That was a slight issue for us because we were assuming effectively that we had a hinge here, so that this would always be in tension. So once that change ran through, we had to go back and redo all our sensitivity studies and make sure, one, that if this did end up going into compression, which it did in some places, that the hanger actually had the ability to compress and keep things apart. And then we fed that through to the facade guys, who made sure that there was enough tolerance in the head detail to make sure that the glass was going to be unaffected.
You take one more question. Shane, yeah.
Was there enough dead weight in the roof to stop reverse tension coming into the front column from uplift?
Everywhere apart from the two corner columns. So the corner column here, because you've got, again, it's 30% of the roof, when there's uplift acting on all of that. And when we looked at sort of semi-fake pattern loading, where we'd have, say, all of the cantilever loaded with wind up and nothing on the back span, that was going into tension. But it's certainly a very conservative case. But we wanted to make you don't want to get to that situation where it's ripped out and going, oh, I should have checked that. You want to just, for the sake of maybe a little bit of extra reinforcement and a slightly thicker bar, you want to make sure you got it covered.
And did you have to check for the fatigue in the connections then with reverse loading, or?
It's not going through enough cycles to make fatigue a problem, and everything was preloaded anyway, so it's all clamped down.